Okay, so can everybody see two screens? Hello? Can anyone confirm me that if I am audible or not?
Yes, ma'am, you are audible and we can see the two screens.
Okay. Whenever if someone feels that I am not audible or any of the screens it's not visible, then please let me know either by unmuting yourself or by writing in chat. And while I'm talking, please keep your mic mute, otherwise it will create noise. So let us wait for another 2 minutes and we'll start from 5 p.m. Okay, so welcome you all to this course, Nuclear Astrophysics. We will take a 8 week journey from today. Today is the first week discussion. Today is 4th March and it will run up to 22nd April 2023. So first, let me introduce this course. The course instructor is Professor Anil Kumar Gaudichetti from IIT Roorkee, and myself is your TA Nilakshi Shanapati from IIT Kanpur. And we will have a problem solving and doubt clearing class every Saturday 5 p.m. to 7 p.m. Okay, so yes, so first thing, okay, let me add everyone, otherwise it is creating problem. Okay. So yes, as I was telling, so this is the first discussion session, and week one I have already uploaded one week zero video in the YouTube channel. And for your kind information, that there will be a YouTube channel. If you miss any class here, or you want to visit something again, then you can visit there and check the videos again and again. So for that, I am sharing the YouTube link here in the chat box. And you can visit the week zero video, that is a short introduction of this course. And then whenever you find that you need to visit this discussion session again, or you have missed this class, then you can check the uploaded video there. And Gmeet link is already shared by Sam Portal with you. And any query you can ask, or by writing your question in the chat box, or you can unmute yourself and discuss with me. Otherwise, there is the ask a question portal in the Sam. There you can always write your doubts, and we are there to help you. So let us first. Okay. Let me wait 5 more minutes because people are still joining and they may miss something. Okay, now I'll start. I'll not wait anymore. Whoever is joining or so, but whoever has joined newly, let me introduce me once again. Myself, Nilakshi Shanapati from IIT Kanpur. I'll be your TA for this course, and there will be a problem solving and doubt clearing class on every Saturday, 5 p.m. to 7 p.m. And right now, if any one of you cannot hear me or cannot see any screen, then please let me know via chat box or by unmuting yourself. So if someone miss these classes somehow, don't try not to miss. But if someone miss, then you can visit to the YouTube channel, and that I have already shared in the chat box. But those who have joined newly, for them I am right. I am giving the link in the chat box once again, and the Google Meet link is already shared with you, via which you will join and we will discuss. And there is a ask a question portal in the SWAM where you can ask any question anytime. And during the discussion, you can write your question in your chat box, or you can unmute yourself and ask me. So, without any further introduction, I will start now. Whoever is joining, please uh, try to catch. And I have already given the details, whichever I am telling as an introduction thing. They can, whoever is joining newly, they can see that in the written pad, that writing pad. Okay, so let me start our discussion. So this is the week one discussion, where you have already known about you have already I hope you have all watched the videos. I hope all of you have watched the videos, and the summary is like this: that you, in first lecture, you have no you we have discussed about historical background, observational astronomy, properties of sun and of stars. Then the second lecture was of properties of galaxies and universe, in some sort of discussion about that. Third lecture was about background of elemental abundance curve. Fourth and fifth lectures was evidence of nucleosynthesis 1 and evidence of nucleosynthesis 2. So these are the basic things that you have already known by now, and you have also solved the assignment 1 question. We will today solve some of the problems which are like whatever you have solved in your assignment 1. It will help you to understand some of the concepts again, and some of the new concepts also, which will be helpful for your examination purpose also. The examination, whoever want to get a certification from NPTEL, the examination is on 29th April, and the last date for registration is 17th March up to 5 p.m. So, what we will learn today? The key concepts which we will learn today is, the first thing is luminosity. We have talked about professor has talked about luminosity multiple times in the course, and you have also get to know this word luminosity multiple times by now. But what is this luminosity? That we will go with some mathematical background. Also, we'll try to see some very basic questions regarding that. Then what is the CMB, cosmic microwave background? That we'll also know, as there may come some questions related to CMB. Then the Hubble's constant we will know, not very deeply, but some, like how to solve some problems and very basic concepts regarding that. And then the abundance of elements, which you have you guys already have learned from the lecture, and I will just discuss some few concepts of it again. And then the HR diagram, that is very important, not only today, but we will discuss about the HR diagram again and again in this due course. But today I will introduce about the HR diagram also. So first, before going to the questions directly, I would like to know that Okay. Which type of question would be asked in NPTEL, MCQ, MSQ, or ACQ? So, sort of, right now, we can't tell exactly about the details of about the MCQ, MSQ, or ACQ, but you can. It is mostly MCQ, and but you don't think that always it will be some theoretical thing. Rather, there may be some mathematical questions also, like numerical questions, using some sort numerical numerical type questions that you may get there. But there will be options, and we will solve some sort of questions, some type that kind of question that you get a glimpse that how which type of questions you are gonna get in the examination. But before starting, I would like to know that there are 35, 32 people, I think, here right now. The background of yours, like, are you from BSc, MSc, BTech, MTech, 12th level? Then it will help. It will be helpful for me to discuss with you in more friendly manner, like how I should tell all these things. So can one by one unmute and tell. I'll tell the name and just tell your name and tell me that what is your background. Okay. First is Ankita Jana. Can you please unmute yourself?
Yes, ma'am. My name is Ankita Jara, and I am from BSc second year.
Okay, thank you. Darathi J. If I am wrong by pronouncing your name, please correct me.
Ma'am, my name is Dharati J. I'm from second UG, ma'am.
Second year, sorry.
Second UG, ma'am.
Okay,
Physics.
okay. Then Devika.
Hi ma'am, I'm Deviga and I just completed my BSc in physics.
Okay, Gayatri Kupusami.
Yes, yes.
Sorry, I
My
can.
name is Gayatri.
Yes.
My name is Gayatri. I'm BSc second year.
Okay. Godhulipal.
Good evening, ma'am. My name is Godhulipal and I am pursuing Masters in Physics,
Okay.
second semester.
Okay. Hajara K.
Yes, ma'am. My name is Hajara from Kerala, Calicut. I'm a PhD holder in nuclear physics, ma'am.
Okay. And Harshini K.
Myself, Harshni from Lady Do College, second year BSc Physics.
Okay. Ishan Chakraborty.
Hi, I am Ishan, and I recently completed my BSc Physics Honours degree in 2022.
Okay. Jamuna P. Hi, Jamuna. Okay. Next, Jenat Sajid.
Hi, ma'am. I am Janet. I am pursuing my MSc Physics first year.
Okay. Monisha Rajkumar. Manisha.
Hello. Hello,
Yes.
I'm Manisha. I'm a teacher in physics
Hmm.
and starting to teach nuclear astronomy, astrophysics, and cosmology. That's why I have chosen this course.
Okay, sure. Nanda Kumar B.
Ma'am, good evening, ma'am. I am Nanda Kumar, third year BSc Physics, ma'am. Thank you, ma'am.
Nupur Bagwe. Yes, Nupur. Okay, I can't hear you. You may write in chat box. Parvati KH.
Hi ma'am, I'm Parvati. I'm a first year MSc student.
Okay. Pintu Kanthar.
Hello, ma'am.
Yes.
My name is Pintu Kanthal. I am from Kolkata, West Bengal. I completed my MSc in physics.
Okay. Thank you. Prithvish Agarwal.
Hi ma'am, I am Pritvish. I am a first year master's student in physics.
Okay. Priyane. Priyan. Raja Shekhar.
Hello, madam. Good evening. I'm Rajshekhar from Faculty of Physics, madam.
Okay. Then Raman JP.
Good evening, ma'am. I'm R. Darshana, second BSc Physics.
Okay. Sai Ramakrishna.
Good evening, ma'am. I am Srivatsav. I am studying integrated MSc third year.
Okay. Sam Chintapalli.
Good evening, ma'am. I completed my degree in physics and currently I'm free. I'm applying for MSc in physics.
Okay. Sami Yukta.
Good evening, ma'am. I am Samyukta, second BSc Physics.
Okay. Sangavi.
Good evening, ma'am. I'm Sangavi, second BSc Physics.
Okay. Santosh Kumar.
Good evening, ma'am. I am Santosh. I have completed MSc in physics.
Okay. Satya Shuji. Sorry, Satya, I can't hear you. We may write in chat box. Shirshendu Roy.
Hello, ma'am. My name is Shishandura, and I am pursuing my second year of MSc of Physics.
Okay. Shivangi Tiwari. Shivangi. Okay. Saurabh Natta. Okay, I think you have written there. Okay. So you are physics honors third year, 6M. All right. Okay, you are Shweta. You are second year BSc Physics. Nupur, you are first year BSc Physics. Okay. Then who is left? Sugandha Khangar.
Good evening, ma'am. I am Dr. Sugandha Khangar, Assistant Professor in Physics, Shivaji Science College, Nagpur. I am recently teaching the nuclear physics and interested to study the concept of astrophysics. That's why I have joined the nuclear astrophysics.
Okay, great. Okay, Satya Shuji is BSc Physics second year. And I think Ishwarya is, she has joined later. Otherwise, everyone is done. Okay, so yes, it was very nice to know you all, and I am very. It's very nice that all of you have a very good amount of physics background, and we will certainly enjoy this course. Though I found this course is pretty preliminary, but yes, we will discuss. We will enjoy this course. So yes, and I have shared two screens. Whenever you find to go to the question and again come back to the solution, I will write in the solution writing pad, and the question will be appearing in these slides, where I will show some of the images or some things also, but that will be that is mostly for the key concepts and the questions. But whatever I will be solving here, the problems, that will be in the writing pad. So I will try to give I try to keep these both the screens in my screen, but if whenever you find that you need to see the question again, or you need to see the solution and solution again, solution screen, then please pin that screen and go there to check that screen only. So, and if anybody finding any issue in that case, then please let me know, or via chat box, or unmuting yourself. So the first question, whatever is there, that is saying that red giants have mass tens of times that of the sun. So before going to the question, there are like we all know that we have, as we have a birth and death period, like we born, then we slowly grow up, and then we die. Same thing is true for the stars also. They are from and they have a life cycle from birth to death. Today I will not discuss about the life cycle and the stages of the stars, but I will discuss about this thing in in due course in the upcoming classes. But as this is a week one discussion, I would like to I have given this kind of questions just to see that if anybody is aware about that how much you know about these things, then it will help me to run that further course. So if anybody knows the answer, or everybody can write into the chat box that that there are four options, which will be the correct answer. The question is, the red giants have mass tens of times that of the sun. They have high, option A, higher surface temperature than the sun. Option B, higher luminosity than the sun. Option C, higher mean particle density than the sun. Option D, lower core temperature than the sun. So these are one slide. I will just to start this session, to do some interaction, I have given such kind of questions. Whoever is finding to answering it, please unmute and talk with me. Otherwise, you can write it in the chat box. Then I will start further discussion and solution for further problem solution for solving the further problems. So yes, take your time and please come up with some idea or some answer. That what do you think?
Hello, ma'am.
Yes.
I can zoom the question, the yellow page. Actually,
Yes.
I can't clearly
You can't clearly
see the questions.
You can't
See the questions.
Okay.
The question is not visible. The slide is not visible.
Okay. Somehow I wait a minute. Wait a minute,
Ma'am,
please.
the question is clear. The yellow, some yellow short
Yes. Can you
box by
please
box.
wait a minute? I just want to check that what has happened with the question thing, like that with the writing pad. That is not visible, right?
Yeah. I want to see. Actually, I want to see in my laptop the whole pages about the question so that I can see it clearly.
Mhm. Mm. Change layout. And,
Yeah. Now it's okay.
all right. And,
Yeah, all right.
And can you see the writing pad? I think no. Can you?
No, the writing pad is not visible.
Okay. Now? Now can you see the writing pad?
Now the writing pad is visible, but the situation is just like before.
That will not be visible. I will do like whenever I will be writing, I'll come to this writing pad and then I'll go back to the slide for the questions again. All right?
Okay,
And
ma'am.
maybe I can write the questions here also. That will not take much time. So the option A was higher surface temperature, temp, then sun, high luminosity, then sun, C, high mean particle density, then sun, and lower core temperature, then sun. And many of you have already, I think, started answering it. So 1A, 1B, 2A, I can see the slide. Question 2D, 1C. Red giants have, Godhuli is saying, red giants have lower surface temperature than sun and higher core temperature than sun. Okay. Any other answer from anyone else? Then I will answer it.
Higher
One
luminosity.
C, high mean particle density than sun.
Okay, and what Monisha is saying?
B.
Okay. So the right answer is also B, like higher luminosity than the sun. So in the first lecture also it was talked about the luminosity and mass of the stars, and there it was hinted that it is related with each other. And in this case, red giants have mass tens of times of the sun. That means mass is equal to 10 times of mass of sun. And red giants, if you see the HR diagram, then will clearly it will give you the idea that the luminosity of the it will have the higher luminosity than the sun. And to know that, I have given the question for that purpose only, that you will get the idea that how much the HR diagram is important in case of stellar astrophysics, that it can give us the idea of luminosity, temperature, surface temperature, luminosity, mass at the same time. And this is some of the parameters are correlated with each other, and some of the parameters are observational facts which we have as a HR diagram currently. So these are the the correct answer is obviously B. And how we are reaching to that, you will get the clear idea when I will discuss about HR diagram. But at this moment, just remember this. You can remember, or like take it as a information that it has high luminosity than the sun. The next question is and some mass of the sun and all those things are already are already there in the lecture 1 or 2, I guess, on lecture 1 I think. But still I am writing the details of sun radius, of what is the mass of the sun, and density of the sun, because all of the things whichever we will be discussing, those will be on the basis of sun temperature, surface temperature, or sun mass, or sun density, or sun temperature. So the it is very important to remember, or to get a note, take a note of these parameters. What is the value of these sun's parameters? So these are like our sun, that is the radius of the sun, that is 6.96 into 10 to the power 10 centimeter. 696 000 kilometer. Then the mass, I also don't remember these things. You can keep a note, and for exam purpose you need to remember these things, but it is not so obvious that it will be so easily be remembered. So maybe I think in examination also they will give the value if you need to solve by putting them. Otherwise it will just be on the in terms of R sun, or M sun, or T sun, like that. So density is 1.4 G by centimeter cube. T at surface, T sun at surface is equal to 5800 Kelvin. I am writing this as T sun at surface because the variation is obviously there. So right now 5800 Kelvin is for the temperature of, at the surface of the sun. And luminosity is 3.83 into 10 to the power 33 arc per second, equal to 2.39 into 10 to the power 39 MeV per second. I hope my handwriting is clear to all.
Yes, ma'am.
Okay. And yes, so these are the values for the sun. And now let's move to the second question. So question 2 was, some of you have already started answering, but let me write the question, and then I see that what you guys have already started answering, and we'll discuss again about that. All right. So the second question is, Sivangi is saying, Sangavi is saying one request. I am not apply to the SWAM, but the last date February 6th. What I do, ma'am? So are you talking about the registration or registration into the course or registration into the examination? If it is registration into the examination, then you can register up to 17 March 5 p.m. But if you are talking about the course registration, that thing, I think it is already been done, but I don't know if it is possible to join at this moment, but I will try to find out the part. I mean, I will by next class maybe I can give someone's mail ID if you can contact and tell them directly to join you into the course. But for that, right now, I am not sure exactly to whom you have to contact. Maybe I'll check and let you know by next class. And okay, so the second question is, white dwarfs are smaller than the sun in size. They have a lower surface temperature than the sun, b lower luminosity than the sun, c lower mean particle density than the sun, d higher core temperature than the sun. So what it is telling, white dwarfs are smaller than the sun in size. They have lower surface temperature than the sun, lower luminosity than the sun, lower mean particle density than the sun, higher core temperature than the sun. So now you should be able to answer this question, as I have already give some hint or told something about this in the first question. So think it and choose the option wisely. Everyone try to answer it, so it will be helpful. It does not matter if you are wrong or right. It is just a discussion, so don't be shy. Okay. And all, most of you is telling that it is B, and you guys are absolutely correct that the answer is B, the lower luminosity than the sun, as white dwarfs are smaller than the sun, and it is for the HR diagram. You will get it easily. If you know about that, you will be getting it easily. Otherwise, obviously, we will learn that. So it's very nice that you have understood about heat from the problem 1, and you are in right track in problem 2. So yes, the next question I will go, but before that let me show you something. Maybe we can discuss about something, then we will go into the next question. So I think let us discuss the question. Then I will discuss about the thing. So the question 3 is, you all should answer this question because this has already been discussed in class, and it is very popular thing like in our daily astrophysical discussions. So the question is, temperature associated with the universal CMB, that is the cosmic microwave background radiation, is, should I give you the option or anybody can answer? Okay, somebody has already answered it and he is right, but still let me give you the option that 0.7 Kelvin, 1.7 Kelvin, 2.7 Kelvin, some random, D 3.7 Kelvin, E 4.7 Kelvin, and so on. It does not matter. So you guys all know that it is 2.7 Kelvin, 76 Kelvin. Very nice. So, but anybody has any idea what is cosmic microwave background? Now we will discuss about this a bit. Can you see my slide now? Okay, so I think every one of you, I mean, most of you are familiar with this diagram, and this is the cosmic microwave background that I have taken from the ESA Planck CMB from the Planck data. Uh, so this is just, this picture is telling you about the afterglow that we got after the Big Bang happened. So this CMB is like the fluctuation in the temperature that is still present, and we can see this via our radio eye. If we see something with our optical telescope, then we see our sky as dark night, dark sky, nothing is there. But if you see via radio telescopes in sub-millimeter or millimeter order, then you will be able to see there are some glow, like the dark sky is showing some glow, and that is what was the first notion that what is this. And after finding the cause, now we know this is a cosmic microwave background, which is the afterglow of Big Bang, which is still present, and this is the one of the strongest proof of of the Big Bang model. Still, there are many debate, but this is one of the very good like observational aspect which help us to know about the know about the some sort of that we are in the right direction, we are knowing about the universe in our in correct way. So this is the cosmic microwave background picture. You must have a familiarity with this thing, because as we are all astrophysics enthusiasts, then you will obviously many a time will get to know about get to see these things. And this cosmic microwave background is there is lots of studies have been done in few the past 3 decades maybe, for the CMB, and now we know many things about the cosmic microwave background. And for that, the main thing that we need to know is the radio astronomy, which takes the main part to improve the cosmic microwave background science. So the next thing is that, and that was the question what we have just discussed now. I'll not go further details about the cosmic microwave background, because this is just not a radio astronomy course. Rather, we need to go more towards the main topic, that is the nuclear astrophysics, which we are discussing here. The next question is very important, interesting, and it will give some idea of Hubble's constant, as well as some idea of problem solving, that what kind of problem you can get in your examination. So the question is telling that the absorption spectrum of calcium usually shows a line at the wavelength of 3934 angstrom. It is observed to have a wavelength of 4002 angstrom in a distant galaxy. Assuming Hubble's constant to be 7 km per second per megaparsec, the approximate distance of the galaxy from the Earth in megaparsec is what? First, let me ask you one thing, that everyone aware about the astronomical distances like parsec, light year, megaparsec, all these things? If anyone does not know, please write into the chat box or unmute and tell. Then I will discuss those things in next class. So within another 1 minute, if you don't tell, then I'll assume that you guys know that thing, or otherwise please tell me. I'll be very happy to discuss in next class those things then. So I think everybody is aware about the cosmological okay. MPC is megaparsec, and 1 parsec is equal to, yes Santosh, you are right, 3.26 light years, and 1 megaparsec is another 10 to the 6 into 10 to the 6 parsec. So 10 to the 6 into 3.26 light years. So that is the thing. But do you guys know about that, how parsec is calculated, and light years is all right, but how parsec and these things are visualized, how we calculate those things? If you know, then it is all right. If anyone don't know, please tell me, then I'll discuss those things maybe in next class, obviously. Only Sam has talked that he or she, I forgot, he has don't know about this, he does not know about this, but apart from that, nobody is telling anything. So I hope everyone is aware about these things. Please feel free to tell me, otherwise I'll. Yes, somebody, you are right, you are again right, that this is like that only, parsec is angle subtended by the 1 AU, so you know, you have the idea. But Santosh is telling how it is calculated, man. That is, so I will discuss this next class within 5 or 10 minutes, and that is very simple idea. So right now you just get the thing that parsec PC. Okay, let me share the this thing, the writing pad. Then I am stopping this, and okay. So PC is written. PC is the short form of parsec. MPC, that is the short form of megaparsec. LY is the short form of light year, and these are the astronomical distances. So these are the astronomical distances, and we will definitely see this how to calculate this in next class. Somebody has written something. Ma'am, if we have such a question like question number 3, then we will take only the correct answer, or it should be shown in the exam paper. No, it will be computer based examination, I think, as far as I know. So I think it will be just tick mark type question. Like you have to choose the correct answer only. This is all right. So now let us start discussing about the question 4. The question 4 is telling the absorption spectrum of calcium usually shows a line at the wavelength of 3934 angstrom. It is observed to have a wavelength of 4002 angstrom in a distant galaxy, assuming Hubble's constant to be 70 kilometer per second per MPC, megaparsec. The approximate distance of the galaxy from the Earth in megaparsec is, let me give you options if anyone is calculating, 43, B 53, C 63, D 73, E 83, F 93, or in megaparsec unit. So this is the question and these are the options. Like let me clearly state the question once again. Like the absorption spectrum of calcium usually shows a line at the wavelength of 3934 angstrom. It is observed to have a wavelength of 4002, that is 4002 angstrom in a distant galaxy, assuming Hubble's constant to be 70 km per second per megaparsec. The approximate distance of the galaxy from the Earth in megaparsec is how much? Okay. So Monisha has already answered, and if anybody is calculating, please calculate it. Then I will solve it. And in that due time, can you please Monisha unmute yourself and tell me that how did you solve it? Manisha.
Okay, I have calculated the redshift. Then from the redshift, I have calculated the recessional velocity. And from the then applying Hubble's law, V is equal to HT, I calculated D.
Okay, great. So you are all right with the process. Let me wait for others. If everybody please try it once, then I will solve it. Okay, Manisha. So let me state the question once again, and then I will solve. The absorption spectrum of calcium usually shows a line at the wavelength of 3934 angstrom. Okay, so let me write it as lambda 1 is equal to 3934 angstrom. It is observed to have Ma'am, if we don't write the answer of some numerical question in the exam paper, the answer may be wrong, then what should I do? Without evidence, it is not possible to say which answer is correct, which answer is wrong in MCQ type question. Sorry, sort of, I did not get the point. Are you talking about that how to understand that if answer is right or not? For that, you will be provided with a scribble pad where you will be writing you will be solving the question on yourself, and you will get the answer. If you are right, then it will be among the options, and whatever the right option you are thinking, if that is right, then you will get marks after ticking that. And obviously it is MCQ and numerical type, so you don't have to randomly click any answer. No, it is not like that. You will solve, obviously you will solve in your scribble pad as a numerical problem is usually solved, and then you will provide the answer, that is just give the tick that will be there in the computer. So if that is correct, then you will get the marks, and if it is not, then you will not get the marks. Is this all right, sort of? Otherwise, I think whatever I understood your question, that I feel like that to answer. And Sangavi is
Ma'am, on top, ma'am.
yes. Who is this?
Fourth question, once recall, ma'am.
Sorry, is this Sangavi? Who is talking? Please.
No, ma'am.
Who is talking? Please tell me. Okay. What are you telling? Whoever was talking, please tell once again. I did not get your point. What you were talking about?
Ma'am.
Yes. Yes. Okay, I'm not getting what is the problem and who is talking. So yes, Sangavi is telling that please help to me, ma'am. What help do you need? Are you talking about the problem? Then obviously I will solve it right now by discussing it.
Ma'am.
Yes. Yes, whoever is talking, please
One
tell.
more recall, ma'am. Fourth question. I not.
Okay, I am discussing. I will just discuss
Ma'am?
now. Yes,
Yes, ma'am.
I will just
Thank
discuss
you.
now. I will obviously discuss now. Sudhikin Pramanik is telling that can we watch the recorded session later on? It will be helpful if you join the live session, obviously, so that you can discuss with me and also with the other friends, whoever is taking this course. But if somebody has any problem, obviously you can check it in the YouTube later on, and all the videos will be uploaded in the YouTube channel. That is in that the link I have given into the chat box previously also, and now also I have given that, shared that. So that is my official NPTEL channel where the videos will be uploaded. If somebody and if you want to visit
Okay,
these
ma'am. Thank
concepts
you.
again, then you can visit also. Okay, so I will now discuss the question 4. Like the absorption spectrum of the calcium meteorite shows a line at the wavelength of 3934 angstrom. It is observed to have a wavelength of
Thank you, ma'am. One second.
okay. It is observed to have a wavelength of 4002 angstrom in a distant galaxy. So lambda 2 is 4002 angstrom. So now I am gathering all the information that is provided there in the problem. This is the way you will solve in your examination also. Then I will tell that what are the key things that is already mentioned in the question. So now it is telling that assuming Hubble's constant to be 7 kilometer per second per megaparsec. Hubble constant is 70 kilometer per second per megaparsec. Now the approximate distance of the galaxy from the Earth. You have to find out the distance. Now this lambda 1 is the actual thing that you should get, and lambda 2 is the 4002 angstrom, that is the observed thing that you are getting. And why is this happening? Because there is redshift into the picture. So when the light when the wave is propagating and all the things, like if the wavelength is there and it is like this kind of thing is happening, it is more stretching and it is
Is
going
where,
towards
ma'am?
more wavelength, then it will be red shifted, and if it is going towards smaller wavelength, then what we get is the blue shifted thing. So is anybody talking anything? Do anyone want to share
Nothing, ma'am.
anything or ask anything? Yes, please. Yes, please tell.
Madam,
Yes.
am I audible?
Yes, you are audible.
Because some reason my laptop's microphone is not working. I joined with my through my phone. So my question is, in the examination, that if any numerical question came, which has lots of options, so if examinations and providers, they will provide us any board or any paper where we solve the
Yes.
solution and then take on the
Yes.
right, which is right or wrong answer. So I cannot understand your previous reply. So can you tell me?
They will provide you some papers or scribble pad where you will write or you will solve on your own, and you will get the answer if you are right. And whatever answer you will get, then you will tick that answer only.
Okay, thank you, madam. Okay.
So yes, so the thing that I was telling, that the actual wavelength, that is 3934 angstrom, and the observed wavelength is 4002 angstrom. So that means it has redshifted. And I hope you guys are aware about some sort of idea about red shift and blue shift. But if somebody feel like you don't know, then also please let me know, because when I yes,
Ma'am,
yes, yes, tell me.
once related, once related this questions exam, related with question exam.
Sorry. Sorry, I did not get what you want to point out. What is your question? Please tell me. Okay, otherwise I will go. Like, I'll continue my solution. Like, there is a red shift and blue shift. Like, if you, I will just go through this shortly now. But if someone wants any detailed discussion about this, then also please let me know, that I will again discuss in next class. But suppose if you have something which is going further away from you, then what we will see is red shifted. Like, the wavelength is increasing, and you will see some there is the wavelength which you are observing, that is towards the higher wavelength, or towards the higher wavelength, if it is going away from you. And if it is coming towards you, then you will see that something is getting towards blue shift, as it is getting to the shorter wavelength. So that is a basic, very like layman idea of the red shift and blue shift, to get some sort of notion that if it is going away, and if it is Ma'am, speak in Tamil. Actually, this course is for everyone of all over India. So we are meant to be talk into English only. So uh, that is that is the thing.
Ma'am, I'm not in understand, ma'am. Please speak in Tamil, ma'am.
Tamil is not possible. Actually, there are like this course is taken by everyone from India, and there are very from the various parts of this of India. So every people are there. For everyone, it means to be talk into English only. The courses has designed in such a way, and the videos which you are seeing in the NPTEL portal, or whatever discussion will be carry forward, that all will be in English only, and I'm really sorry for that.
Okay, ma'am. Okay, ma'am. Thank you, ma'am.
Hmm. So the thing.
Okay, ma'am.
Okay. The next question. The question is, how do we know the true wavelength emitted by the star? The thing is that in the question it is already mentioned to you, the absorption spectrum of calcium usually shows a line at the wavelength of 3934 angstrom. Here we are here in the question, it is already, we know the absorption spectrum of the wavelength, what is emitted by the absorption spectrum of calcium. As we already know that, that's why we can see that it is shifted towards these red shifted or blue shifted. And if you want to talk about that, how do we know, apart from this question, that how do we know the true wavelength emitted by the star, then the main thing is that everybody is emitting in every wavelength. The thing what we see in our eye is the optical spectrum only, because that is the visible range which is visible to our eye. But everything is emitting, almost all the thing are emitting in almost all the range in throughout the EM spectrum. And at the end of today's class, I will talk about the EM spectrum, and what is what are the objects there in the universe, and all of the stars, and what they are emitting. They are actually, if you observe a star in optical wavelength, you will see it some part of it, and you will get some idea of it. If you observe it with a radio telescope, then you will observe then you will get some other information about it, because it is also emitting in the radio as well as emitting in the optical. But the notion we have, that we can see in optical. That's why we are saying, oh, we usually say this is red, green, or whatever, and whatever you images are seeing, those are mostly false colored images. So don't think that star can emit only in one wavelength. No, that is not true. It has a broad spectrum. It emits in many wavelengths. Okay. But as and what about the raw image? Raw image, whatever image you have, that is a set of data. It's set of data set that you have. You are doing the post processing, you are doing the photometry, you are doing all the things, and you are giving the false colors to understand. There is nothing about like you what understanding we have apart from optic. If you are seeing in optical range, then you can see that. But if you are not seeing in optical range, apart from like some radio range or some x-ray or any other range, then there are no notion or no idea to us that what it is. We have just a set of voltages, or which is the measurement of the intensity, and then we are doing the data processing, and we are doing all sorts of things. There are many pipelines to process it, and many things like I can't summarize that in a single line or single paragraph. There are many post process. After doing all those photometry things, then you will get the image, and whatever color we give there, that is mostly false color image. So I was talking about red shift and blue shift. So I think the idea of red shift and blue shift is not very clear, but some sort of you got the idea that if a lambda 1 is let me be very clear, like if it is there is lambda, some sort of lambda that should be there, and if it is towards lambda plus delta lambda, then it is red shifted. And it is lambda to lambda minus delta lambda, then it is blue shifted. And the lambda plus delta lambda, that is it is going away from you, and if it is coming towards you, then it is blue shifted. Okay. So this is the basic concept that you can get right at this moment. But I if anyone is interested or anyone is not getting the point, then please write in the chat box or let me know by unmuting yourself. I will again discuss about this in next class. So now let me go to the problem. By now I think you have you may have forgot the question, so let me go through the problem once again. The absorption spectrum of calcium usually shows a line at the wavelength of 3934 angstrom. It is observed to have a wavelength of 4002 angstrom in a distant galaxy, and assuming Hubble's constant to be 70 km per second per megaparsec, the approximate distance of the galaxy from the Earth. So now we know the redshift blue shift concept. So the difference that, so we know lambda 1, we know lambda 2. So lambda 2 minus lambda 1 is the delta lambda, that is equal to 4002 minus 3934, which is 68 angstrom. And the lambda which should be there, that is equal to lambda 1, that is the absorption wavelength of calcium, and that is equal to 3934 angstrom. That is the true thing, like what it should be. So that is we are considering lambda. Now the red shift is del lambda by lambda, then it is 68 angstrom by 3934 angstrom, which is 0.017. Okay. And this is equal to, so you can understand this z, the red shift, that is equal to delta lambda by lambda. That how much, that what does it mean? Delta lambda by lambda, delta lambda means how much it is shifted wavelength by original wavelength. So the upper part is also a unit of wavelength, that is the lambda, that is in meter or centimeter, that is in angstrom here, sorry. And the lower half is also in angstrom, that is it is a unit place constant. Okay, so that is again can be written as a v by c, that is velocity is also velocity is something, the unit of velocity and unit of c obviously same, they are all velocity. C is the speed of light and v is the velocity, so this is also a constant unit less number. So z is equal to delta lambda by lambda is equal to v by c, which is a redshift. That how now you can have a question that how we can tell that this is a redshift, because what I have told is that how much it is going away or it is going towards me, that is deciding that if it is red shifting or if it is blue shifting. So the shift by the original wavelength, that is what is giving us the constant, and that is also deciding up to the, that is also decided by the velocity, that how it is going far, with the how much velocity it is going far away or coming towards me. So that's by this way you can compare this thing and compare these things like this, and this is actually by definition you can also say this, and this is the thing which you call as redshift constant, and by this way you can calculate z. Now you have delta lambda, which is which is 68 angstrom, and lambda is 3934 angstrom. 1 minute. Okay, extremely sorry. So this is the z, that is the 68 angstrom by 3934 angstrom, that is equal to v by c. So now you can calculate v is equal to zc, or 38 by 3934 into c, that is equal to 0.017 c. So now you have velocity v, and if once you have velocity, then you can get the distance equal to v by h, where h is the Hubble's constant. This is another relation that you can remember, that is v is equal to hd, the relation between velocity, distance and Hubble constant. So where this is the velocity, this is the Hubble's constant, this is the distance. So once you know about this, then you can calculate the d, as you have v and h. V is equal to 0.017 c and h is equal to 70. Now it will be, as it is distance, and it will be MPC. So 0.017 into 3 into 10 to the power 5 kilometer per second by 70 kilometer per second per MPC. So now you can analyze the unit also, like if you cross the kilometer and second, then you will get, let me write it in this way. Second inverse, then second inverse also goes away, then it is only megaparsec. This is the unit of distance. So 0.017 into 3 into 10 to the power 5 by 70 mpc, that is equal to 72.85 mpc about. So it is about 73 megaparsec. Okay, now I think many of you have will have doubt about these things also, like how we are writing the relation between velocity, distance, and Hubble's constant. This relation you can. That's why I'm telling that you should join these discussion sessions, and if you are not able somehow, then you should check the YouTube video. Then you will get to know these things which are not discussed in the class, in the videos, which will be discussed here in the live sessions, and that will be very useful for your examination purpose and to learn the concepts. So this is the relation that Hubble's constant, which is the relation between the velocity, distance, and the Hubble's constant, and which tells about the universe expands and the rate shifting thing. That's why we are calculating the velocity also from the rate shifted thing, the shift wavelength, from the shift wavelength, and we are getting the idea that how we are calculating the distance from this. So from now on, if you have this kind of question, then you have any idea about the shifted red shifted or blue shifted thing, then, and you know the Hubble's constant, that is a constant uh, which you know, which will be given obviously to you, then you can measure the distance of the galaxy very easily. This is one way nowadays by which you actually calculate the distance of the galaxy. Because what you do is that you are doing spectroscopy of a distant galaxy, like you have a galaxy, and you are doing you have a galaxy there.
Hello, ma'am.
Yes.
Hello,
Yes.
ma'am. You already put the value of c is 3 into 10 to the power 5. But c is the velocity of light, and its value is 2.99. That is 3 into 10 to the power 8 meter per second. No? Then how you put this value 3 into 10 to the power 5?
3 into 10 to the power 8 meter per second is equal to 3 into 10 to the power 5 kilometer per second. I have write this in kilometer per second.
Okay, okay, okay.
All right.
Okay, okay, ma'am. Okay, thanks. Okay, okay. Huh.
So if you have a galaxy, then what you are doing, you are getting the like wavelength is coming, wavelength is coming, and you have telescope over there, and you are getting the intensity spectra. From that you are doing the spectroscopy, like you have spectra. Okay, so once you have the spectrum, then by the spectrum analysis, first of all you can do that what are the elements that is emitting over there. If it is emission spectra, if it is absorption spectra, you will see that at which element, which wavelength the wavelengths are missing. That is because the elements are present over there, that's why they are absorbed. Then you can get the absorption spectra. That is nice. But from the emission spectra or absorption spectra, after doing the spectroscopy, then then you know that what is the actual value of that element that should emit, but what you are getting. Okay, so now you know the actual value of the wavelength and what you are getting, that is a shifted, if it is red shifted or blue shifted, that means it is coming towards us or it is going away, how much distance it is over there. So by using that v equal to hd, finally you can calculate the distance of that galaxy or the thing. So this is a very useful concept as well as a very useful mathematics, which will help you to understand many concepts at the same time. First of all, you are learning about the red shift, blue shift, as well as you are learning about the Hubble's constant, and as well as you are getting the idea of spectroscopy, that how much is it is important, and you are also getting the idea that how you can what is one way to calculate the distance of the galaxy from us. So please practice this kind of problem. The books are already mentioned in SWAM portal, and in the week 0 video also I have mentioned that what are the books you should follow. And please go to the please check the video also to check the books, and also please go to the SWAM portal. They are also written there. So this is a very important problem which you should understand very clearly to get some idea that what is actually going on, how we actually do the stuff. Okay, so I hope you all are very like you have got some idea of numerical problems also, that how what you are gonna get in the examination. Now again, after doing some mathematics, let me go towards the presentation and discuss about something else, because we are already discussed a lots of mathematics and lots of things by now. Okay, so now I am sharing my presentation again. Everybody can see it, right? Hello. Yes. Okay. So this was the question what we were doing at this moment. So we got the answer. It is 73 megaparsec, and we learned about many concepts here. Now let me move towards some information kind of things, where we will just discuss about some meteorites. We all know that meteorites are the falling some old rock that somehow we in the formation stage has come to the earth, fallen to the earth, and somehow it has the ability to tell us about the age of the uh, galaxy, age of the solar system, and how it all has formed, because these are the one of the oldest stars that is there in our system. So that's why we study meteorites, but it is more towards the analysis part. Meteorites analysis part is more towards the geophysicist work. So they work we work together to analyze these as astronomers and geophysicists, all these work together to analyze these and to get the idea that what were there, and from these one of the main thing that we get to know is the abundance of the elements. And this picture whatever we I am showing here is the carbonaceous chondrites meteorite, which is the oldest meteorite, and help us a lot about to guess about our galaxy's age and our solar system age. This is mainly our solar system age. So regarding that, I have one question, that which of the following meteorites play a major role in estimation of the universal elemental abundance. And I think this was also in your assignment one question. So and it was already discussed in your lectures. So everyone should answer this question, and please write in the chat box what do you think. So somebody is asking what is Cl? What is Cl carbonaceous chondrites? There are many categories. There are many these are meteorites, and meteorites have many classes, like Cl classes, S classes. There are many classes. They one of the class is Cl class, and these carbonaceous chondrites is fall into the Cl class domain. And you can easily find out the carbonaceous chondrites in Google, and you will get about the Cl details very easily. I will not go into the details about the Cl carbonaceous chondrites, because those will be not much helpful for this course. And everybody is right. Obviously, everybody is telling that option C. Option C. Yes, it is option C. Carbonaceous chondrite. Now the next thing that I will like to show before going to the next question is that this picture you have also seen in your class lectures. Like this is the elemental abundance graph where you can see that the abundances of the elements is shown in the logarithmic scale in z in y-axis, and z, that is the atomic number, is shown in the x-axis. So from here this curve is important because by seeing just this elemental abundance curve, you can get the idea that which is the most abundant element in our universe, that is hydrogen, and next abundant element in the universe is helium. And you can get subsequently the idea of the how it is falling and how it is behaving, though it is it will change some sort of thing, somewhat in the different galaxies, and if you see the different part of the universe, but it is the trend will always be the same. But one thing is very noticeable here. If you see for the odd number of a and even number of a, that is some difference there, because some of the elements which have the even number of a, that is more abundant than the odd number of a. So for that reason I have given this is another MCQ type question which you just need to know, and you need a sort, not to remember that, you need not to remember the whole spectrum, the whole abundance element thing, that how much is this and how much is that. No, you don't need to remember that. You just need to have the notion that how you can understand by seeing the graph that how much element is there present in which element is present there in which amount. That means you should have the idea of analyzing the graph. That is one very important thing, and that is what that is the main thing that for which I have given this graph here. You don't you can, but these are the like very these are the some pretty basic information which you can remember, is that hydrogen helium, that is the most abundant thing in our universe. And next is that if I whatever the question is telling, that which of the following is true for isotopic abundance for elements, and there are five options. It has also been discussed in class, and I hope you can answer this question also. The five options are: odd a isotopes are more abundant than even a isotopes are more abundant than odd a does not affect isotopic abundance, odd z elements are more abundant than even z elements, odd n elements are more abundant than n even n. N is a neutron number, Z is the atomic number, and A is a Z plus N. Okay. So let you guys answer it, and I will see that what you guys are telling. You guys have already started answering it. Everybody is saying 6B, 6B, 6B. Yes, even A isotopes are more abundant than odd A. You guys all are right, and yes, that is the answer. So as you guys can answer these questions, and these are pretty basic questions which have already been discussed in class, so I am not writing these again in my writing pad, rather which need to be discussed, that I will write again. Okay. Next question is, which of the following shows correct abundance of elements? Option E, A is telling hydrogen 92%, helium 0.06%, oxygen 0.1%, C 7.1%, and B and B, C, D, E, F, you have six option here. All for all, hydrogen is given as same, but the helium, oxygen, and carbon, they are given as different. It is also discussed in class, and I will not go through the options. Please write your answers, that what do you think. and this is also discussed in class actually, in the lecture. Please don't feel shy, anyone. Everybody right. It does not matter if you are right or wrong. By the in the process, you will obviously learn. Okay. People are still answering. Okay, answer it. I will then discuss. Somebody has raised his or her hand. Do anyone have any question or anything to say? If not, then yes, most of the persons are right. It is option B. Sorry, it is option C. It is option C that yes, hydrogen, helium, oxygen, carbon. That is the correct order. Yes, hydrogen, helium, oxygen, carbon. That is the correct order, and the correct answer is C. Hydrogen is 92%, helium is 7.1%, oxygen is 0.1%, carbon is 0.606%. Okay. Okay. Yes. Yes, you guys are all right. The hydrogen, then helium, then oxygen, then carbon, and the percentages are like 92%, 7.1%, 0.1%, and 0.06%. So now the next question, where we'll see some pictures and some popular science discussion, as we all like astrophysics and we all are very familiar with this. Okay, Godhuli, everybody has started telling the answer of 8. Very nice. Yes. Which one of these is the site of production of lithium, beryllium, and boron, and that is a cosmic ray spallation. And I think this was also there in your assignment 1. But I chose this answer to discuss because there are many things to discuss here. Okay. The first thing is that Big Bang. Though this is not the answer, but we need to know about these things. We should discuss some sort of discussion, at least some big picture we should have. So Big Bang is there. I have given this picture. This is the very popular Big Bang picture. So there is nothing like, no, the answer is not A. The answer is E, cosmic ray spallation. Okay, but I will discuss all of the thing one by one, just to give a big picture notion to you. So the Big Bang is uh, okay. So the Big Bang is that a model, it is a cosmological model. This is nothing like something bloom happened and everything has started, the universe formed. Those are some popular science notion, but if someone asks what is a Big Bang, this is actually a cosmological model, and by some pretty weird manner it has named as Big Bang. So this is just, if somebody asks what is Big Bang, then it is a cosmological model where we try to understand that how universe forms and how universe expanded over the time, and how it is formed as per it is now, and how it is going to evolve in future. So that is the study of the Big Bang cosmological model, all the cosmological models, and one of the successful model is Big Bang model, and CMV is one of the candidate which helps us to understand that Big Bang model is more towards truth, like it may be the right thing. So that is that is what I wanted to mention about Big Bang. Now let us go to the next thing, that is the stellar interior. I think this picture is pretty small to understand all the notation, but yes, this is what it is showing as is the interior of the sun. Sun is also a star, and this sun is this is a main sequence star. At this moment, this is a main sequence star, obviously, and our sun, the how the interior of our sun looks like, that is shown here. And if I go through this, then at the center of the sun, whatever is there, that is called the core. Then we have the radiative zone, then we have the convective zone, then we have the photosphere, then we have the chromosphere, then we have the corona. And if someone asks, and this photosphere is the actually the surface which we actually observe, which we can actually see, which we see in our naked eye. We can't see chromosphere and corona. Chromosphere and corona is actually the atmosphere of the sun. And if somebody asks that how much corona is extended pretty large, like it is extended, the atmosphere of the sun is extended over, like you can say that we are also in the corona of our sun. So this is that much expanded. So we don't we still sun is one of the sun is the thing, that star which is nearest to us, and we can observe it directly, we can see, and we can do analysis, and we can pretty much, we can do many things with it. That's why it is a open laboratory to us to understand the interior or the atmosphere of any kind of main sequence star. This is also a nice laboratory to study the plasma physics. So these are apart from that, there in this picture, the sunspots, granule, penumbra, umbra, solar wind, flares, everything is shown. Flares are the events that when the solar eruption happens, then we get the flares. And solar wind is one of the big hazard in our life. Like there are some eruption happens, and there are lots of charged particles which are coming towards the coming out from the sun towards the planets. And solar winds actually come. And we also nowadays it is also a very popular thing, like for a current for a one decade, for the past decade, like to predict the solar wind, then when next solar wind will happen, and how we can protect our earth from the solar wind. And this is solar wind, the solar wind and all these things are one of the cause that why we are seeing the aurora borealis and all those things. So sun earth effect is another important aspect which we can see in our daily life, which we are with which we are affected also. And the sun is the most nearest star, so we can study our sun much better. So these are the this is the solar interior. So any case, as it is a main sequence star, so any kind of far away star that is there in our that is not in our galaxy, or maybe in our galaxy somewhere else, then we can also consider that maybe those kind of stars, those stars will also have the same kind of interior. That's how, by studying the sun and studying these things, we can study the stellar interior also. Okay. The next thing is whatever I am showing is a Crab Nebula. This is also a supernova remnant which is running into the currently running into the with the blower of the pulsar of the crab pulsar. And at the center of this Crab Nebula, we have a crab pulsar. Actually, we have a pulsar star, obviously. And this is very famous picture. And this is a one of the pretty big pretty good nebula picture that we have currently. So this is just very popular, as well as you have to know about the crab pulsar. Crab pulsar is one of the most important pulsar and most studied pulsars till now. So, and this crab nebula is fueling by that crab pulsar. So this is one of the most interesting thing for the astrophysicists or astronomers to study the crab nebula. So that is another thing. So that is another thing that I wanted to mention. So the apart from that, now the last but not the least is cosmic ray spallation. As we are interested here in nuclear astrophysics, so that is it is our main thing that we will discuss now. Not very details, but in very short manner. That what is cosmic ray spallation? Do you know what is spallation? Do anyone have any idea of spallation? Yes, no, no. Okay, so the right question first to ask that what is spallation. I think you can see the video. Is it visible to you? The video is visible to you, no?
Yes.
Okay, okay, thank you. Yes, so this is like a collision process, like as you can see there. The collision may be such kind of that kind of thing. Like if something is coming and it is just getting it's hitting it and going in the other direction, that is the first option. Or otherwise something it is coming and going passing through it and it is breaking it. Both of by both the processes, the some sort of new particles can generate. As you can see here that this is this is coming, this is hitting, this is going, but they are generating something. And this is coming, this is breaking, this going towards that direction, and it is breaking to something. So in both cases there is generating something, and this is a mechanical process which is done by the which is just happening due to just this is just a mechanical process that I am showing you just to understand what is spallation is. It is nothing but some sort of collision and interaction. Maybe not collision, collision is a very mechanical thing, but maybe you can see as it is some sort of interaction. So that is the spallation. And if you talk about the cosmic ray spallation, then it is a naturally occurring nuclear reaction, that is interaction. Nu- uh, as it is, these are the cosmic rays which like if you consider this ball as cosmic ray that is coming, and there is some material in the universe or some things which it is hitting, then with the process of nucleosynthesis it is producing some sort of chemical elements after after interacting with it, and that is what is called cosmic ray spallation. I hope this thing is clear. I hope this thing is clear. If but if you want to know what is nucleosynthesis, then nucleosynthesis is that is already been discussed in the class. But still, if you want some definition, then I can say that nucleosynthesis is a process that creates new atomic nuclei from pre-existing nucleons. Obviously, there were some nucleons of some atoms. Now it is breaking and creating some new atoms of some new nuclei. That is just the new chemical elements creating after some nuclear reaction. That is the nucleosynthesis, and it is happen and this nucleosynthesis is the cause to create the cosmic ray spallation by interacting between two things. And the cosmic ray cause spallation when and this is just telling that another point, that cosmic rays cause spallation when a ray particle impacts with matter, including other cosmic rays. That is what I was talking about also. So this is the cosmic ray spallation. I hope you can get some visualization that what is the spallation called. And if it is a mechanical process, now apart from mechanical process, if it is happening some nuclear process, some reacting process, some chemical process, then whatever it will happen due to the cosmic ray and matter interaction of that, then it is cosmic ray spallation. Is it clear?
Yes, ma'am.
Okay. Now the very important thing, but I think I'll not be able to discuss very in details about HR diagram today, because only 8 to 10 minutes is left. I'll start from HR diagram again, because this is a very important and very basic thing and very important thing, interesting thing, which you need to know. So I will just maybe start today, but details could not be cannot be covered by today. So first, let me go to the question. If you can, if anyone can answer that, which of the following is true for HR diagram? First point is stars are distributed uniformly on HR diagram. Option B is about 20% of the stars are on main sequence. Option C is all the stars are either on main sequence or below it. Option D is all the stars are either on main sequence or above it. Option E, red giants are above main sequence and white dwarfs are below main sequence. If red giants are below main sequence and white dwarfs are above main sequence. Can anybody answer it? I don't it is not mandatory to answer it, because I should go. I will tell lots. I want to tell lots of thing about HR diagram. But if anyone can answer it, then write it. That's great. Actually, everybody can answer this. So yes, the answer is E. The red giants are above main sequence and white dwarfs are below main sequence. So do we all of you have any idea of HR diagram? You can tell yes in chat box or unmute yourself. Maybe you can write in the chat box. Okay, so as far as I am seeing your answers, that you have some sort of notion about it, and you guys are pretty good at that. I can understand that. But yes, it needs a detailed discussion that I can feel. So maybe I will not discuss that today, because it will take some time. Yes, Godul is telling it is a graph showing luminosity versus temperature. Hmm. Yes, but there are lots of things regarding HR diagram, and this is very one of the main thing, and this is in the stellar astrophysics. It is very important. We will discuss about that. Then this I will certainly I will. I'll go to the next question and discuss. That is also you just an informative question, but I want to discuss HR diagram in great details. Do you guys want to discuss it today, or you will like to discuss it in detail in next class? I mean, it will be helpful if I discuss it in much more details in next class. Okay, okay, sure. That will be good, I think. So the last question, I'll go quickly and end wrap up today's session. The last question is telling CMB radiation is highly isotropic, varying less than one part in temperature over the entire area of the sky. So CMB radiation is highly isotropic, varying less than one part in this this amount of temperature over the entire area of the sky. Can you understand the question? The question is telling that what fraction if you have the total amount, then within that amount one part is telling. Now you have to tell that within how much amount that one part is only varying, and you already know that CMB is very isotropic medium. So now uh, if anyone is willing to answer, please answer it. That can you get the idea that what it is telling, and what do you think? I'm extremely sorry. I just lost my connection somehow. Okay, the question is telling like CMB radiation is highly isotropic. That is the information given to you. Now, varying less than 1 part in temperature over the entire area. So let me write it if to let me write it. Let me stop sharing this and write it. Okay, Purna is telling, ma'am, I missed my assignment one. I was not aware of the last date. How much assignment we should do out of 8 weeks to apply for examination? If you, yes, 6 assignments, that's correct. But if you have missed one, please try not to miss any other. Then you will be obviously be allowed to write the examination. And from next onwards, try not to miss. Okay, and we will discuss obviously. Hmm. Now the last question what I was discussing is question 10, that is CMB radiation is highly isotropic, varying less than 1 part in temperature over the entire area of the sky. And option given to you is A 10, B 100, C 1000, D 10,000. Now the thing is, it is asking is like it is given like there is the total amount of this thing is given. From that you are if you want to get some notion that how many percentage it is varying for the thing, like if this one part is varying for how much part of it, like it is a entire medium CMB. Now the it is given that one part will be affected for how much part, how much percentage. The answer is in percentage, you can tell it in percentage or whatever, or in the fractional form. But the thing is, for how much part the one part is affected, the one part will be affected for how much part. Okay, so that is what it is asking that varying less than 1 part in temperature over entire area, and what is that amount of area. And I think this is all right, this is another information type question, so the answer will be 10,000, the D, option D, like one part is varying for 10,000. That, and why I was specifically uh, uh, focusing on this thing, that this point, that CMB radiation is highly isotopic. This is telling that how much isotopic it is, like only one part is if one part will affect for this 10,000 part, if one fraction will just change for the this whole amount of 10,000 amount of thing. So that means it is telling that how much isotopic it is. So this will be the answer, that it is 10,000. The CMB radiation is highly isotropic, varying less than one part in 10,000 in temperature over the entire area of the sky. Okay. So this was the last question, but now let me shortly brief that what we learned today. We learned about first thing is we learned about one more thing. Just let me check one thing. Okay. So one thing today I missed, that is I wanted to discuss one more thing, that is the luminosity, which before discussing it I have discussed the questions, which was your first two questions, but it is another important topic that need to be discussed. So that will be in discussed list. Let me remove this. So what we have discussed today is that point 1 is CMB, cosmic microwave background. Point 2, Hubble's constant, and lots of, and not lots, but how Hubble's constant, and how to, from using that, how to calculate distance. Then fourth thing which we learned is abundance of element, and some idea of meteorites. Some idea of meteorites. Fifth thing is number 5 is cosmic ray spallation. And these, and lastly what we were discussing about the CMB itself. So this is the summary, week 1, that you have learned. Now what we will learn next. Next we will learn about we have also discussed about Big Bang and nebula and solar interior. So we have discussed many things today, and what are the next things to learn in next week, that is week 2. We will learn first, we will go to luminosity, that I wanted to cover today, but today I could not, so I will cover it in next class, obviously. That is an important thing. Then the second important thing is HR diagram. Now the third thing that I will now apart from that I will discuss again some revision, some new concepts, some new concepts. Some new concepts and some division. But these are the very important two things that we will discuss in next class. So it will be a very important class next week, and these are the things that we have learned today: CMB, Hubble's constant, how to calculate distance of galaxies, abundance of elements, and some idea of meteorites, cosmic ray spallation, a detailed analysis of that, Big Bang, nebula, solar interior. What are these? A big picture notion of these things. So I hope today's class was very helpful to all of you, and you all have enjoyed and learned something. Was it all right for you? And how was please feel free to write anything, that if you are all right with this or not. Okay, thank you. Thank you, everyone. Nice to meet
Thank
you
you,
all.
ma'am.
Okay, thank you. Nice to meet you and talk to you. We'll discuss more and enjoy the course. All right.
But is
Thank
very
you, ma'am.
good, ma'am. Thank you, ma'am.